Welcome back to another section of Chapter 5. In this section, we're going to be looking at something called the fundamental theorem of calculus. This comes in two parts, and it relates the derivative and the integral and sees how they're connected to each other because they are very much connected. Um, and so, and in this, we're going to start being able to find the areas of these things algebraically. We're not going to have to add up a whole bunch of rectangles anymore using geometry. We will be able to start using calculus to find the exact values of these areas under the curve. So let's take a look at the first part of the fundamental theorem of calculus. It says if f is continuous on a closed interval, and then the function I, it's I because it's the integral function. So the integral of f of t, or the integral of f of x, is a to x of f of t dt. This t here, it's called a dummy variable. It's just kind of sitting there. We don't actually use it. It's just a placeholder for other stuff. Anyway, it has a property. It's continuous and differentiable on that interval. Moreover, because who doesn't like to use opportunity to use the word moreover, the derivative of I. Notice here we have the derivative of the integral. It equals f of x. What we do is we take these t's and we replace it with x. Couple things to notice here. The lower bound is a constant, and the upper bound is a variable. That's very important. And so this part of the fundamental theorem of calculus has two very, very distinct implications. The first is a conceptual one. What it says is that the integral is an antiderivative. That's what it is. It's an antiderivative because the derivative of the antiderivative, they cancel each other out and you get back to the function. So the other implication is a very, very direct one, and that's problems just like this. Now, these problems tend to start out really, really like stupidly easy. But they do get a little bit tougher, not a whole lot tougher, but they add a twist to it that is what gets people. So starting out, what do I mean by stupidly easy? Something like this. We have the derivative of an integral. The lower bound is a constant. It does not matter what that constant is. It can be negative, positive, zero, decimal fraction, big, little, does not matter as long as that's just a number. To the x, we're just going to replace the t's with x's. So this will be 5x squared plus 4x minus 1. That is the end of this problem. That's what I mean by it's really easy. We just replace the t's with x's. Done. Where I say that it can get a little twist in it is what if we have something like this? We still have a constant on the bottom, but now we have more than just x on top. We're going to replace the t's with whatever is up there. So we'll have a square root of e to the t, which is now 3x squared minus 1. And then plus 3x squared minus 1, because there's a plus t. And now that's where people stop when they don't want to get the problem correct, because there's another t. There's this one right here. We need times the derivative of whatever it is we're plugging in. Up in this first problem, that was just times 1. But now we actually have something we can take the derivative of and get something more interesting. So we have the square root of this stuff, and then times the derivative, 6x. There we go. And so that's the part that gets people. You have to plug it in, but that's everything, including the derivative. There are always a couple problems like this on the AP test, by the way. There's usually a couple in the multiple choice, and then a lot of times there's a part of a problem in the free response has this. A lot of times free responses are about 4 parts long. One of those parts is this. It's usually worth like 1, 2, or 3 points, depending on the problem. So these could be easy freebie points. Let's look at another one. In this case, my variable is on the bottom instead of the top. If you remember the properties from yesterday, we can switch that around. Last time, we can switch it around, make it negative. This will be negative d over dx times the integral from 5 to x cubed, t to the 4th plus 1 to the 1/3 dt. Now we can plug it in. When we do that, negative just kind of follows along. T to the 4th, well, that's x cubed to the 4th. Remember, when we have an exponent of an exponent, we multiply. So that's going to be x to the 12th plus 1 to the 1/3 times dt times that derivative, which would be 3x squared. All right, so that's the first part of the fundamental theorem of calculus. It's plugging it in, but in the fundamental theorem, this first part, notice every single time what we're doing is we have the derivative of the integral, derivative of the integral, derivative of the integral. It's this derivative of the integral that is what the first part is. The second part is going to deal with just the integral itself, but we won't have that variable in there. So what the second part of the theorem says is that if f is a function that's continuous on the interval ab, and the derivative of capital F equals f of x, so that means that capital F would be an antiderivative of lowercase f. The integral from a to b of f of x is f of b minus f of a. What this says is we're going to find the antiderivative of this, plug in b minus plug in a. And that's how we will find definite integrals. So let's see what these could look like. We have negative 2 to 1 x squared dx, an antiderivative of x squared. That would be, we'd have an x cubed, and we have to divide by that, so 1/3 x cubed, and we're going from negative 2 to 1. That end piece is just notation saying we're going to be plugging stuff in. It's where the bounds go. It could be on the edges of a square bracket as well. Either way, it's notation, it's just how your work gets shown. But now we're going to plug in these numbers. So we'll have 1/3 times 1 cubed minus 1/3 times negative 2 cubed. 1 cubed is 1 times 1/3 is 1/3 minus negative 2 cubed is negative 8 times 1/3 is negative 8/3, so that'll be a plus 8/3. 1/3 plus 8/3 is 9/3, which is also called 3. So that's essentially what we do when we find the antiderivative. Could it become a little bit more difficult? Sure, the antiderivative could be a little bit harder to find. The numbers could be a little bit harder to plug in. That's really all that can happen. Right now, the antiderivatives are going to be just directly from the derivatives that we've been finding. Later on this chapter, we'll figure out how to find harder derivatives than that. But we could have things like cosine of x dx. We're going from 0 to pi over 6. What would give us a derivative of cosine? That would be sine of x. And we're going from 0 to pi over 6. Now, you might be thinking, and in fact, you actually should be thinking, wait a second, he forgot the plus c in that first one. You don't need it for this. For the indefinite, you need it, but for the definite integrals, we'd have this plus c, and then minus blah, 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 plus c. That negative sign distributes, plus c's cancel every time. So with a definite integral, you actually don't need plus c, just with the indefinites. So the derivative of sine is cosine, so the antiderivative of cosine is sine. We're going to plug in pi over 6 minus, plug in 0. Sine of pi over 6 is 1/2. Sine of 0 is 0. 1/2 minus 0 is 1/2. All right, so that's one with trig. How about 1 over x? What gives us a derivative of 1 over x? That would be natural log of x. It's from 1 to 2. We're going to plug in 2, so we'll have natural log of 2 minus natural log of 1. Natural log of 1 is just 0, so this equals natural log of 2, which there's a number in there. It's natural log of 2 is just a number, but that would be the exact value. Finding the number in this case is an approximation. We don't need an approximation. We want an exact value. Another type of thing you can do here is, I went a little bit low there. Let's erase a little bit of that. There we go. And so another thing, find the area under the graph. We've been finding areas under the graph. We're just going to make an integral. We could even be given a graph to look at. Look at that. We're going to find that area exactly. So what gives us a derivative of e to the x? Wait, that's just e to the x. And so we're going to have e to the x from -1 to 1. We're going to plug in 1 minus, plug in -1. E to the 1 is e, minus e to the -1 is 1 over e. That would be the exact answer. If we found a decimal approximation to that, e minus 1 over e is going to be about 2.35 or so. Probably 2.350 something. But the exact answer is a lot of times what we're going to be looking for. We could find the approximation using the calculator. We already know how to do that. But remember, you don't always have a calculator. And sometimes the exact answer is the right answer and the approximation is the wrong answer. So those are the two parts of the fundamental theorem. We do have a little bit of application involved, which is stuff that we've seen. It's interpreting the integral where we're taking the integral of a rate of change. The same stuff we've done. The integral, remember, or the rate of change, the derivative, is the rate at which it's changing. The integral is the total change over that time period or over that interval. And when I'm saying total change, that would be a displacement type of total change, not a distance type of total change. And not necessarily talking about distance, but the idea of displacement versus total distance. So if we're looking at this, we could have something like the population of the United States is growing at a rate of, here's the derivative, p of t, or p prime of t, is 2.867 times 1.009 t million people per year, where t is the number of years since 2015. Look at that, a recent date. It's not since t is the number of years since this book was written in 1972. So we're going to find the derivative. Part A, find the derivative from 0 to 5 of p prime of t dt. This part, this would be given to us, like this is the question. So to do that, we're going to go from 0 to 5 of this 2.867 times 1.009 to the t dt. Find the antiderivative. Remember the antiderivative of something to the x? The derivative would be something to the x times natural log of that something. The antiderivative is the something to the x or t divided by the natural log of that something. And then this 2.867 is just going along for the ride. That's a multiplied constant. So that's the antiderivative of that. We're going from 0 to 5. Now when we plug it in, we can actually pull out these constants so we don't have to deal with them necessarily on the inside. So we could have 2.867 over natural log of 1.009, then times, we can plug in 5, 1.009 to the fifth, minus plug in 0, 1.009 to the 0, and then we simplify. The 1 to the 0 is just going to be 1. The 1 to the fifth is going to be something different. This type of question right here would not be one that you would be expected to do without a calculator. That would be pretty much insane. So at this point, you just plug it into a calculator. You get that this is going to be about 14.661. If my estimations are, I use a calculator. So that is the antiderivative. Second part of the question, interpret it in the context of the problem. That would be the growth of the population over those 5 years, from 2015 to 2020, because that's 5 years. That is the growth. It does not tell you the full population, but it tells you that it grew by that much. That's the issue with the whole plus C's disappearing. We don't have that actual value. We just have what's that change in that value. However, part C, let's say it was 320 million people in 2015. What's the projected population in 2020? It gives us a starting value. To find the ending value, all we need to use is addition. Just add that to what we found. 320 plus 14.661 is 334.661. And then make sure you answer in the context of the problem. Context means I should be able to read your answer and know what the problem was asking. So there are projected to be about that 334.661 million people in the United States in 2020. And so that would be a context type of problem. Notice we're doing the same stuff, and then this part, we've done that the past couple sections. We've been looking at that. That's not changing. The idea that, oh, hey, we just need to add it to a starting point might be new, but it's also a pretty basic idea. But this is what we're doing today. I will catch you next time. Until then, keep working problems, keep asking questions, and as always, happy mathing.